Hi, here we will discuss about the support vector margins. The mathematics behind the margins is given in this session. Consider linear separable data uh, given in this plot. So the data is able to separate linearly. So now we are applying the linear SVM model to make this data into two classes, so which is called binary classification with labels. Here data point label is mentioned with y and features are denoted with capital X or x1 x2, because we are having the two features here, x1 and x2. Then the output is represented here as two classes, one is negative class and positive class. So the data which is available below the hyperplane is called negative class, and the data which are available above the hyperplane is called positive class, which is represented -1 and 1. Sometimes they will use 0 is the negative class and 1 is the positive class. So the hypothesis function for linear combination of inputs mentioned with h of x with respect to parameters w comma b represented as w transpose x plus b. So this can be extended as here w1 x1 plus w2 x2 plus b. So here the w1 for parameter for feature x1, w2 is parameter for x2, and this is the bias which will be take care of w0 in the SVM hypothesis function. So we can uh, predict the output for given sample is denoted as y dash of the particular sample I, which is denoted as sign of hypothesis of the sample I with respect to parameter w and b is given as -1. That the data point I will be negative class whenever the predicted value less than 0. That means if you take particular data point in this plot, suppose this data point here, when you are predicting the value for this sample I by our SVM algorithm, if it is giving the value less than 0, that means for example -5, then which is less than 0, so this data point belongs to negative class. Suppose another one ith sample number, suppose you take 3, x of 3 with respect to parameter w comma b, if it is predicted as +1, which is the hypothesis of h of x of I. Ith sample is sample number 3, then parameter w, parameter b, if it is greater than or equal to 0, which is assumed as positive 1. For example, if you take this data point, if it is predicted greater than or equal to, suppose its value is 12, so this is greater than or equal to 0, so this will be assumed as the positive class, which is denoted above the given hyperplane. So this is the way we can categorize the given data point based upon the prediction in SVM. Here the variable b performs the role of w0, and w takes the role of w1 etc into wn transpose, because here we are having the w transpose x in this, the w in the sense the combination of all the w parameters, x in the sense combination of all the features, given input features. So this is the intercept for the hyperplane. In this plot, let's consider x represents the positive training samples, which is represented as y equal to +1, and circles are represented as negative training samples -1. The descent boundary is the line because we are having the features two dimension. So here we are having a line. So the equation is W transpose X equal to 0. So here the hyperplane always will have the equation. This equation will be W transpose X plus B equal to 0. Below this W transpose X plus B will be less than 0. Above that, above this hyperplane W transpose X plus B greater than or equal to 0. So that is the representation of this plot. Here we have taken three data points A, B, C. So here we have taken point A, point B and point C. Then the point A is observing very far from the decision boundary. The point A is here very far from the decision boundary. So when you are looking that point A, which is always, yeah, the data points are perpendicular to the hyperplane. So this is each data point is assumed as a vector. So this vector will have the direction and also magnitude, direction and magnitude. So the magnitude is this length of the data point from the hyperplane is the magnitude. This angle is the uh, direction of this data point. So here when you are observing A is too far from the decision boundary, uh, during the prediction the value of the A will be estimated as +1 because the uh, the A is greater than or equal to this hyperplane 0, this hyperplane 0. So that's why, which is in the positive class. Then when you are looking at the point C, data point C, this one which is very close to the decision boundary, assume its predicted value hypothesis of X is 0.1. 0.1 also greater than or equal to 0. So which is predicted as a positive class. That means 1. So now when our hyperplane is slightly changing. So our hyperplane is, suppose in the next iteration, if next forthcoming iterations, if it is coming like this. So when it is coming like this, so here the data point is appearing below the hyperplane. So this hyperplane is now, this data point hyperplane, this is less than 0. This data point is appearing in the position of less than 0. So which is now appearing in the negative class. Here that small change to the decision boundary making the prediction is in the negative class. So user have more confident about the prediction at data point A and C. So the whenever you are changing the uh, hyperplane position, there is the possibility of changing the data points class. So here which is giving the user to predict the class for each and every data point. In this plot, we have given the two-dimensional data here, which is the support vector for the negative class. So here this line is W transpose plus B equal to -1. This hyperplane is drawn by using the support vector this data point. So which is W transpose X plus B equal to +1, and the hyperplane the is always W transpose X plus B equal to 0. So here the data points which is having distance between the negative hyperplane and the decision boundary. So this distance is negative margin, this distance is positive margin. So the total distance is this one, this distance is mentioned with 1 divided by norm W, 1 divided by norm W. So this distance is 1 divided by norm w. So we are having two distances, so 1 plus 1 by norm w in the positive positive hyperplane, that is the distance between the positive hyperplane and hyperplane, plus and distance between negative hyperplane and distant boundary. So it will be taken 2 divided by norm w. So here which is mentioned in the mathematics, so w transpose x2 plus b equal to uh, plus 1 positive class, here positive class this support vector. So here we look at this, we are giving the data points, this is x2, this is x2, so this one is, this data point is x1. So w transpose x2 plus b is positive class, so this is the data point which is acting as a positive class x2. W transpose x1 plus b equal to minus 1 acting as a negative class. When you are applying the arithmetic operation, you will get the 2. So x2 minus x1 is the distance between x1 and x2, right? So this is the distance between the x1 and x2. So here the w transpose is called normal vector. It can be written as w transpose divided by norm w x2 minus x1. So finally it can be written by 2 divided by norm w. So here norm w already it is mentioned here. Yes, this is given here, how that 2 divided by norm w came, right? So this is the distance, this entire distance is the 2 divided by norm w, right? So we have to maximize this distance with respect to the objective function w transpose x plus b greater than or equal to 1, or w transpose x plus b less than or equal to minus 1. So here because we are taking the minus 1 is the negative class, positive 1 is the positive class. The common objective function is here w transpose x plus b, here equal to I mean hypothesis of x equal to w transpose x plus b. This is the common objective function. This is the function which is used as here constraint. This function is used as constraint in this support vector machine to optimize the SVM model. To optimize the SVM model, this function is used as the constraint. So this is the mathematics behind the SVM to maximize the marginal distance between the support vectors. Thanks for watching.